Okay, let's go. So during the previous session, I have finished the previous session with a proposition making the link between arbitrage opportunity and local arbitrage. Okay? So let's remind this definition. Okay? So a financial strategy this way. Okay? That is an adapted stochastic process with values in R to the power d plus 1 is an arbitrage opportunity if it is self-financed, important condition to be self-financed, okay, and if I start from 0, so P almost surely or everywhere in this course it's equivalent, okay. V capital T is always positive, and the probability for V capital T to be strictly positive is strictly positive. So I express everything in actualized value typically because divide or not by a strictly positive quantity, change nothing, okay, in my inequality. So this is an arbitrage opportunity, okay? So what we have done concerning this, we have seen in particular that if I don't want an arbitrage opportunity in my market, okay, this is equivalent to the following formulation. Calligraphic K intersected with L0 plus of omega Fp is equal to, is reduced to 0. Why? In fact, it's a tautology in some sense because it's just come from the definition. Here, you have the set of the possible final value of self-finance strategy starting from 0. If you impose it to be positive, then necessarily it is equal to 0 if you don't want such a strategy to occur. Okay? So it's something we have already proved together. Okay? And I have finished the previous session with the definition of a local arbitrage. So I take T belonging to 0, T minus 1, so excuse me, it starts 1, capital T, and we say that C is a local T arbitrage if I have two conditions that are fulfilled. C scalar product between ST minus 1 is something that is always positive and strictly positive with a proba that is strictly positive. And of course, this one has to be Ft minus 1 measuring. So intuitively, okay, here I have a global notion between 0 and capital T, and the notion of local T arbitrage is something that happens between T minus 1 and T. Okay, it's a kind of strategy only between T minus 1 and T, in such a way that I never lose and I have real opportunities of profit. And the result we are going to prove now, it's something that I have already stated in the previous session, is that the global notion of arbitrage opportunity or absence of arbitrage opportunity is equivalent to the fact that there are no local T arbitrage for any T in one capital T. Okay? So it's what I have stated as lemma 4. That is NA is equivalent to NAT for all T belonging to one capital T. And I have already said that the interest of such a proposition is that when you are going to deal with multi-periodic model, it is equivalent to consider the problem of absence of arbitrage opportunity globally from 0 or capital E, or to focus only on two consecutive dates in the model. Okay, so you can do a local reasoning in order to deduce something that is local, in fact. Okay, so let's do the proof of this result. So one implication is obvious, and the other one is a little bit less. So during the 4 next session, we have 1 hour and a half. Okay, so arrive at 3. Okay, please. Okay. I said that this side is not that complicated. Saying that if I have no arbitrage opportunity, I have no local T arbitrage. Let's suppose the contrary. Okay, so suppose that if there exists a local T arbitrage. Okay, so in order to prove that A implies B, I prove the contraposition no B implies no A. Okay, so suppose that there exists a local T arbitrage. We are going to prove that in fact if there exists a local T arbitrage, I have an arbitrage opportunity. So why I have this? So if there exists a local T arbitrage, I will be able to build an arbitrage opportunity this way. So we consider the following self-financed strategy. So we have seen together during the previous session that in order to define the self-financed strategy, it is equivalent to define its initial value and the quantity of risky assets. Simply, yeah? The quantity of non-risky assets is a byproduct by the self-financed condition. So we consider the following self-finance strategy. Okay, so the one starting from 0, and for the quantity of risky assets put in my portfolio, I can take h of s that is equal to c, indicator function that s is equal to t minus 1. So what is the meaning of this one? So xi is an ft minus 1 measurable random variable with values in r to the power d. So it represents intuitively quantities of risky assets. Okay? Here, I define a strategy that is self-financed. I impose its initial condition and the quantities of risky assets. Okay? And what are my quantities of risky assets? But it means that if I am not at time t equal to t minus 1, I do nothing. I will only do something between t minus 1 and t. Okay? And what I will do between t minus 1 and t will be to do exactly xi, my local T arbitrage here. So if I have this one, what is the final value of this strategy? You know that you have a general formula for the value of a self-financed financial strategy. Okay, it's what I have called the discrete H as capital T. And in this situation here, I have in fact a single non-zero value that is for S equal to T minus 1. For the other instance, okay, my quantities of risky assets are equal to 0. So here, I obtain simply C S T minus ST minus 1, in fact. And so, by the fact that C is a local T arbitrage, so if there exists a local T arbitrage C, okay, defining this thing allows us to find an arbitrage opportunity, implying that I have proved that this side occurs. A implies B was proved, proving that no B implies no A by contraposition. Okay? So if I have no arbitrage opportunity, I have proved here that there are no local T arbitrage. But it is not the interesting side, in fact. What will be interesting for us in practice will be more this one. To fulfill that I have no arbitrage, I have only to check that I have no local T arbitrage for any date between 1 and capital T. Are you okay with this? So you need to be okay with the definition we have previously introduced, as I have said previously. It's not that complicated if you have in mind, okay, all the things I have previously defined. So, for the other implication, in fact, to do this, we are going to do an induction on the number of periods on the market by induction on capital T. So capital T is my final date, okay? And we are going to prove this result here, making an induction on, if you want, the number of periods in my model, okay? So if I want to initialize what happened for t equal to 1? For t equal to 1, I have a model with only one period. For t equal to 1, I have a model with two dates and one period. Implying that if I have only a single period, these two notions are equivalent because I have a single period in my model. So to be local or to be global in this situation give rise exactly to the same thing. Okay? So if I have only one period in my model, no problem, because the definition of being local or being an arbitrage opportunity coincide in a single period model. Okay? So now, but the idea is now to prove the heredity in the induction. So to pass from t minus 1 to t. Okay? I initialize my reasoning and then prove that if it is true with a t minus 1 number of period, it will be true for a number of period equal to t. So my induction hypothesis here is what? Is that what I want to prove, that is this implication, is okay in the market with final date capital T minus 1. So my induction hypothesis is that, okay, I have NA of T, okay, for all T belonging to 1 T minus 1, implies NA in the market with final date T minus 1, okay? This one. So this is my induction hypothesis. And what I want to prove is that, okay, if it holds with this hypothesis, it will be okay for capital T. Okay? So I want to prove this one for capital T, supposing that I have my hypothesis, my induction hypothesis. So in order to prove what I want, that is this one using my induction hypothesis, we are going to suppose the contrary. So we are going to suppose that there exists an arbitrage opportunity in the market with final date capital T, and prove from my induction hypothesis that I will obtain necessarily in this way a local T arbitrage. So what I have to prove? So if there exists a local, an arbitrage opportunity in the market with capital T periods, we have to prove that there exists in this market a local T arbitrage. t belongs to 1 capital T. So I have my induction hypothesis, and it's what I want to prove. I repeat that using my induction hypothesis, I want to prove this implication. To prove this implication, I suppose the contrary and prove that, okay? So I do once again the contraposition reasoning here. So if there exists an arbitrage opportunity denoted by HT hat in the market with T period, we have to prove that there exists in this market a local T arbitrage. Okay? That's what I have to prove. So I start from an arbitrage opportunity, this one, and I have an induction hypothesis that I have to use. My induction hypothesis is something that holds for the market with final date capital T minus 1. And here I work with something that is with a final date equal to capital T. So as usual, when you do an induction reasoning, you need to make a link between the value at time T minus 1 and the value at time T. But I am able to do this because an arbitrage opportunity is a self-financed financial strategy. Okay, we have a self-financed financial strategy. So we know from what we have done in the previous session that there is a link between the actualized value at capital T and the actualized value at time T minus 1. That is exactly this one. Okay? And if I have an arbitrage opportunity, what I have that V0 is equal to 0, V capital T is positive, and the probability that V capital T is strictly positive is strictly positive. You have here, there exists an arbitrage opportunity that is this one, and that fulfills the relation between its value at time T and its value at time T minus 1. Okay, so I know that this one is positive. The problem is that from the fact that this one is positive, a priori I can't deduce what are the signs of this one. It can be everything, okay? So that's why we are going to introduce the following. We are going to introduce the set capital A. That is the following set. This one. The set of the W belonging to omega such that the value at time T minus 1 is strictly negative. Okay? What can you say concerning this set? I know my value is an adapted process. So I have a pre-image here. So I have something that belongs to F capital T minus 1 because the value of a financial strategy is something that is adapted to my filtration. Okay? So I have this one. What we are going to do now is just to consider the following. So I start from my equality here. And I just multiply in both sides by the indicator function of A. I have this one. So what I have if I do this? If I do this here, I have something here that is positive. Here, I have something that is always negative by construction because my indicator function is 0 or 1, and when it is equal to 1, Vt minus 1 is strictly negative. Okay? So I have something that is negative here and strictly negative on capital A. Okay? Something that is always positive from the fact that V capital D is positive itself, and I multiply by an indicator function. And this one, by construction, is always negative and strictly negative on capital A. You agree? And now, well, I know that in some situation I am able to say what is the sign of this one, because I have this property here. But I just have to be careful because for this set, a priori, I don't know if it has a probability that is strictly positive or not. Maybe I have something of proba 0, and if I have something on proba 0, it means that this one doesn't appear, and you may have, okay, all the things that are in fact 0, and I am able to say nothing in this situation. Okay? So we are going to consider cases. First case. If I have P of A that is strictly positive, what can I say? So keep in mind what we want to do. I start from an arbitrage opportunity. I want to prove that there exists a local T arbitrage in the market with capital T periods. So if I am in the case where P of A is strictly positive, are you able to find on the blackboard here an arbitrage, a local arbitrage? In fact, a local capital T arbitrage even. Which one? If you say yes, I'm agree with you. But which one? Have a look on what I want to obtain here. My local T arbitrage will be given by this here. So if I take C equal to the indicator function of A, ht minus 1. First of all, I know that capital A is ft minus 1 measurable. So I have a random variable here that is ft minus 1 measurable. Because this one is, and I multiply by the indicator function of a set that is in f capital T minus 1. So I have f capital T minus 1 measurable, and what can I say? Well, I can say that C st minus st minus 1, this one is positive, this one is negative, so of course this one is always positive in the large sense. I have always this one. But it's not enough to have the definition of a local T arbitrage. I have also to prove that the probability that this one is strictly positive is strictly positive. But it is the case. Why? Because here P of A is strictly positive. When I am on A, this one is strictly negative. If I want this one to be positive, this one has to be strictly positive. So I can say the following. The probability that my quantity here is strictly positive, that is this one, I am sure that it is greater than P of A, that I have supposed to be strictly positive in my first case. So it means that in this first case, I am able to prove that what? That Xi is a local T arbitrage. Okay? So I don't have finished the proof, because for the moment my result holds in this situation, because if I don't suppose this one, I am not able to conclude here. Okay? I need my P of A to be strictly positive. You agree? So I start from an arbitrage opportunity. I prove that in this case, I build a local capital T local arbitrage. Okay. So the second case I have to deal with it's the case where I don't have this one. That is what happened in the case where P of A is equal to 0. Okay? A probability can be 0 or strictly positive. I have only these two cases to deal with. P of A equal to 0. What is the meaning of P of A equal to 0? So it means that the probability of the complementary set is 1. What is the complementary set? Vt minus 1 positive. So if P of A is equal to 0, it implies that Vt minus 1 is always positive. Okay? Vt minus 1 is always positive because I suppose that P of A is 0, so P of A complementary 1. Okay. So when a random variable is positive, P almost surely. In fact, I have two possible situations. The case where it is equal to 0 with proba 1. Okay, the case when I am constant equal to 0. In the other case, the case where the probability that I am strictly positive is strictly positive. Okay? So when I am positive P almost surely, I have only two possible situations. The case where the probability that Vt minus 1 is equal to 0 is equal to 1. And another case, that is the probability Vt minus 1 strictly positive is strictly positive. So when I am positive, I am 0 or I am strictly positive with the probability that is strictly positive. What happened in this situation here? If I know that Vt minus 1 is equal to 0, I come back to what I have here. If Vt minus 1 is equal to 0, I have Vt that is equal to Ht minus 1 St minus 1. And what I know about this quantity is positive always and strictly positive with a probability that is strictly positive. So what I have proved in the case where the probability that Vt minus 1 is equal to 0 is equal to 1, I just proved that, in fact, in this case, Ht minus 1 is a local T arbitrage in this situation. Okay? That was exactly what I want to prove. Keep in mind that at the end I want to prove that anytime I have a local T arbitrage. So in the case where Vt minus 1 is equal to 0 almost surely, then this quantity is a local T arbitrage because this one is equal to 0 and I know that Vt is positive and the probability that Vt is strictly positive, so the same all for this one. It is exactly the definition of a local T arbitrage. Now, if I am in this situation here, what I have? I have Vt minus 1 that is positive P almost surely, and I have the probability that Vt minus 1 is strictly positive, that is strictly positive. If you have understood the sketch of my proof, for the moment there is some things that I don't have used. Which one? So I have done an induction, so I have an induction hypothesis. For the moment, I don't have used my induction hypothesis. My induction hypothesis, that is this one. What is the meaning of what I have written on the board here? But here it means that I have an arbitrage opportunity, but in the market with final date capital T minus 1. So here, arbitrage opportunity in the market with T minus 1 periods. Because, okay, I start from 0, my value at Vt minus 1 at time T minus 1 is positive and strictly positive with a probability that is strictly positive. So I have this one. And so I have my induction hypothesis. If I have no local arbitrage in the market with T minus 1 period, I have no arbitrage opportunity in this market. So if I have an arbitrage opportunity in this market, I will have a local T arbitrage. So it implies by induction hypothesis the existence of a local T arbitrage for T belonging to 1 capital T minus 1 at the end. In any possible case, I have proved that here I have a local arbitrage, here I have a local arbitrage, and here I have a local arbitrage if I suppose that there exists an arbitrage opportunity. So I have proved the implication I want. Okay? Well, it's not that complicated, but we have to be careful because, okay, you have hypotheses and cases to check if you want to be rigorous in the proof, okay? The idea is to use this one, that is the key formula if you want, giving a relation between what happened at time t and what happened at time t minus 1 in order to use my induction hypothesis. And then I have to work a little to distinguish between cases, okay? And my induction hypothesis is just used for the final case here. And I repeat that from a practical point of view, this result that absence of arbitrage opportunity is equivalent to the absence of local T arbitrage will allow us to work locally when we are interested in arbitrage opportunities for multi-periodic models. Okay? I will be able to only focus on what happened between two consecutive dates. Okay? Yeah?
Why is the probability of zeta ST minus 1 is greater than the probability of A?
Because of this, if you are on A, you know that this random variable by construction is strictly negative. So this one is strictly negative, this one being positive necessarily, this one is strictly positive, but if you are on A. So the probability that this one is strictly positive is greater than the probability of A. Okay? Other questions? No? So now it closes the generality on this first part of the course, and now we are going to start to first to state one of the main results of this course and the proof of this result. That is what we call the fundamental theorem of asset pricing. That is a deep result, making in my situation a perfect equivalence between the absence of arbitrage opportunity and something that is a statement that is purely from probability theory. That is, in fact, the existence of an equivalent martingale measure. Okay? So it's exactly what we are going to do now. I am not sure that we'll be able to finish the proof today, okay, but I will finish next week. I need, I think, 1 hour and a half to do the proof. Okay? So it will be too short. You have class after, huh? You have stochastic calculus after. Do you have some question, or may I erase the board? Have you tried to have a look on the videos? No? No? How was your impression? Huh? Not that bad, huh? You have also the lectures notes that I have scanned, huh? You can find them. Okay? So I erase. So I will state my result, fundamental theorem of asset pricing, and the proof will be the result of several lemmas that I will do step by step. And if I have to summarize the key argument of the proof we are going to do, the key argument is convex separation theorem. Okay, so it's the first chapter, in fact, what I have done previously was the chapter 0, or generalities, and here, so fundamental theorem of asset pricing. So this is a result that is not that old, in fact. So in our situation here, it was proved by two researchers, Harrison and Bliska, in 1981. Not that old. So 30 years ago. Something that is not that old if you have in mind that the first proof of the existence of the ground motion, for example, is in the first part of the 20th century, okay? In the 19th century. Okay, so let's state and then prove. So it's what I call the theorem 1 here. So that make a link between no arbitrage opportunities and the following. The set of the equivalent martingale measure is different from the empty set, where I define the set of the equivalent martingale measure as the set of the mapping Q from my final sigma algebra F into 0, 1, such that Q is the probability equivalent to P that make, so the Q that are the measure here, such that Q is a probability, so I have F here. Q is from calligraphic F, the final sigma algebra, the one on which P is defined, that is in fact the power set of omega, with values in 0, 1. Q is a probability equivalent to P, and I want that this stochastic process is the martingale under Q. This is what I call the set of the equivalent martingale measure. So this is the set of the probability equivalent to the historical probability. To be equivalent means that they have the same negligible sets, okay? And such that the actualized value, so keep in mind that what is ST, it's the stochastic process dealing with the actualized values of the risky asset. So it's a probability equivalent to P that make the actualized value of the risky asset martingales under Q. Okay? So a priori, I have a notion that is purely financial here, arbitrage, that are special kind of strategies starting from zero, okay, that are self-financed, where I never lose and I have real opportunities of profit, and some things that have a priori nothing to do with finance. Okay. So here, in the framework of this course, we are in the situation where, okay, we can prove the equivalence. Typically, if I am in the framework of the course of Bernard de Meyer, okay, it should be a little bit complicated to obtain this equivalence in great generality. You have always this one, every time, okay, independently of the hypothesis on you on your model, okay. But to prove this, sometimes you have to do extra hypotheses, in particular in continuous time. But in our case, that is discrete time with finite omega, I have a perfect equivalence between, okay, these two notions. Okay? And in fact, to try to extend this result in more and more general framework is still an active field of research. In fact, you have still researchers that work on this topic, adding, okay, more complexity in the initial model, so working with omega infinite, capital T that may be also infinite. For me, I have a finite number of periods, okay. Adding, I don't know, transaction cost inside, or adding dividends, okay. And if you add all these extra features for the model, then you have proof that are more and more complex, that can become very, very difficult. So this one is not that complicated from a theoretical point of view, because it will be based on a single theorem, that is the convex separation theorem. But as you will see, we will have to work a little in order to prove. Okay? So it's what we are going to start to do. Okay? So we are going to start to do the proof of this one, but in order to do the proof, we are going to prove, okay, remind, I don't know, 5 or 6 lemmas in order to have the proof. Okay? I have cut the proof in little parts, okay, in order to make it easier to understand. First of all, a definition. So, what I want to prove is clear for everybody? And keep in mind that this is not that without consequences, because if you remind what I have said at the very beginning of the first session, I have said that, okay, I have a probability that I call the historical probability. But in practice, I don't know it. Okay, but whatever, because the one that will interest us from now on will be the one that are in this set here. And for this one, we are going to be able to describe them, okay, in most of model, without knowing the historical probability. You see that the historical probability here just appear here. I want something that is equivalent to the historical probability, that is a probability that is able to see the same kind of events, in fact. Okay? Something that gives strictly positive probability to the same set. Okay, a definition that will be my definition 8 here. But because if I want to apply the convex separation theorem, I have to be in the framework of the convex separation theorem. So that's why first I define the following set. So I define delta to be the set of the positive and measurable random variable with an expectation equal to 1. So it's the set of the positive random variable, okay, Now keep in mind that here, since f is equal to p of omega, in fact, my measurability condition is true for every kind of mapping. Okay? And I impose to have an expectation that is equal to 1. Okay? Well, it's not a lemma, but I said that delta is convex and compact. We are going to do the proof of this one. So it's not the proof of the definition, but just the proof of the fact that what I have defined in my definition is something that is convex and compact. For the convexity, what you have to say? Convex means that you take, okay, you take y1 and y2, you take lambda in the interval 0, 1, you take lambda y1 plus 1 minus lambda y2. And what happened here? But first I have to be positive and measurable. Something that is positive is preserved by convexity, the same for measurability. And then I have expectation equal to 1. So if you take a convex combination, using the linearity of the expectation, I have my expectation that is equal to 1. Okay? If you take a convex combination of random variable with an expectation equal to 1, the expectation of the linear for the convex combination will be also 1. Okay? So for convexity, nothing to say. You just come back to the definition of what is convexity, and you have exactly what you want. Positivity and expectation equal to 1 is something that is preserved by convex combination. Okay? Clear? To prove compactness, what I have to prove?
The set is closed and bounded.
Why? It's not true every time here. Huh? Compact equivalent to closed and bounded, okay, is not true on every kind of spaces. It is true for spaces of finite dimension. It's exactly where we work with here. Where you are in finite dimension, because here you have something that is, okay, let's say isomorphic to r to the power of the number of elements in omega, as I have already said. So I have infinite dimension, so I will agree that in this case, to prove compact is equivalent to prove that I am closed and bounded. The implication that is always true is that compact implies bounded and closed. The converse is false in general, except for spaces in finite dimension. Okay? So here, because I have infinite dimension, a compact is equivalent to closed and bounded. So why I am closed? So it's a classical result, classical argument here. I have an equality here. So it's, yes, it's what we call the closed condition, but if I want to write it correctly, I can define delta as what? L0 plus intersected with what? By the set of the random variables that have an expectation equal to 1. That is this one. Phi minus 1 of 1, where phi is a mapping from L0 of omega fp with values in R that associate to any y its expectation. So delta may be written this way. Here L0 plus is closed. The set of positive random variable is closed because it's something that's stable passing to the limits. And here I have the pre-image of the singleton 1 that is closed. And what can I say about phi here? It's linear, and what can I say about linear mappings? Why? Once again, because I am in finite dimension. Okay? So, continuous, linear, so continuous in finite dimension. So you have the continuous pre-image of something that is closed, you will have a closed space intersected with something that is closed, and so you obtain that delta is a closed set. Okay? So for closed it's okay. It's okay. For bounded, of course we are going to use the definition here. If y belongs to delta, I know that its expectation is equal to 1, and that y is positive. But what is my expectation in this case? My expectation is just a finite sum here. Okay? So it's the finite sum over the elements of the universe of what? Y of W, probability of the event or the element W. So you have here a sum of positive numbers with a sum that is equal to 1. I can deduce that for all W belonging to omega, Y of W, of course positive because I have this, and less than 1 over omega. Okay? So it doesn't imply that I am bounded here, because I have a bound that depends on W, and I want to make the bound here independent of W, but keep in mind that omega is finite here. So I can say that 0 less than y of omega less than the max of the 1 over p of omega, omega belonging to omega. And I can say two things. The max exists because omega is finite, so it's just the max between a finite number of numbers. And this max is finite, okay? But because I have supposed that p of omega is strictly positive. I have said to you at the very beginning that it was important to suppose that the probability of each element in my universe is strictly positive. If it's not the case, I remove this element from my definition of omega. It was to conclude this way here. Finite because the probability of each of them is strictly positive, and because I have a finite number of elements in omega. So I am convex, okay, closed and bounded. So I have something that is compact. Okay? So delta is compact. Do you agree with this proof? Questions? Okay, yeah?
And 0 is linear?
What?
You're saying linear, so it's closed?
Linear, so continuous. C0 continuous. Okay? Because I am in finite dimension. The linear mapping, when this space here is a finite dimension, is necessarily continuous. So I have the continuous pre-image of a closed set, so it is closed. This one being closed, delta is closed. Okay? So why I have introduced delta? Because I have the following results. I have the following results. The no arbitrage hypothesis is equivalent to say that calligraphic K intersected with delta is equal to the empty set. So I have said to you that we are going to use the convex separation theorem. I will remind the statement just after, but with this formulation of NA, I will be exactly in the setting of the convex separation theorem. The case where I have two closed spaces, one of them being compact with an intersection that is empty. Okay. And I remind you that calligraphic K is the set of the final values of self-financed financial strategy starting from 0. Okay? So let's prove this equivalence. What we have already done together is the following. We know, we have proved this during the previous session, that, and I have reminded at the beginning of this one, that NA is equivalent to the fact that calligraphic K intersected with L0 plus is reduced to 0. It's something that I have already proved, and that was, okay, what I have called, don't remind, lemma something. It was lemma 3, okay? So what I am interested in is to prove that these two are equivalent here. These two are equivalent. Okay, so what I want to prove, I will put it in orange. So since this one is equivalent to this one and I want to prove this one, I have only to prove that I have this one. So let's do, it's not complicated to do this. So first of all, so you have fixed calligraphic K here, and you have delta and L0 plus. I have a link between this one. One is included in the other here. Delta is a subset of L0 plus. Okay, so I have delta that is included in L0 plus. So of course, I have this inclusion, okay? So which side I am able to prove with this inclusion? Which side in the equivalence I am able to prove with what I have written on the blackboard here? This one or this one? If you want to prove this one, okay, you will have this one that is empty, but the fact that the empty set is included in the set, okay, it's not that new. The other one. I am able to prove this one here, okay, because if I suppose that this one is reduced to 0, it means that delta intersected with calligraphic K is included in 0. But what can I say about 0? I have two possibilities. If a set is included in a singleton, it is equal to this singleton, or it is equal to the empty set. But is 0 in delta? No, because the expectation has to be equal to 1. So the fact that I have this one and the fact that 0 doesn't belong to delta implies that, okay, delta intersected with calligraphic K is equal to the empty set, because it is included in 0 and doesn't contain 0 as an element. Okay? So I have the proof of the equivalence from the bottom to the top. I just keep the definition of delta on the board here because we'll need it to do the other implication. Is it clear? So I have proved from the bottom to the top. Okay? So for the other one, this side, we are going to do using, in fact, contraposition. So we are going to suppose that there exists an element here that is not 0. We are going to see what happens. In fact, that I will have someone in this one. Okay? So if there exists J belonging to calligraphic K intersected with L0 plus, such that J is different from 0, meaning that I don't have this one. Okay? I suppose that there exists an element here that is not 0. So what happened? I have to prove that calligraphic K intersected with delta is not empty. So do you have a candidate to be in delta? So in delta, I have random variables with an expectation equal to 1. When you have a random variable, how to transform it in order to make the expectation equal to 1? Yeah. I define J tilde as J divided by the expectation under P of J. Okay. So why I do this? Exactly to have something with an expectation equal to 1. And why I have the right to do, be careful, because I divide by something, and I have the right to divide by something because I have a positive random variable that is not 0, so its expectation is always strictly positive, something we have already seen in the previous session. When I am positive and not 0, my expectation is strictly positive. Okay, so I can say that J tilde belongs to delta for my argument here. And why J tilde is in calligraphic K? So keep in mind that I prove this side, and I do it by contraposition. No, this one implies no, this one. Okay? So I suppose that there exists an element that is not 0 in this intersection, and I will obtain my result proving that I have an element in this intersection here. So J tilde is an element in delta. Why it is in the intersection? Why J tilde belongs to K, in other words? J belongs to K. And what we have seen about calligraphic K, this is a vector space. So if you multiply by a constant, you are still in calligraphic K. Because J belongs to calligraphic K, and calligraphic K is a vector space, so that is stable if I multiply by a constant. Okay? And you have your proof. That is, if you start from an element that is not 0 in this intersection, I find J tilde that is an element in this intersection here. So I have proved the implication I want to prove. Okay? And I repeat why I do this, because when I am in this situation here, I have the intersection between two sets that are two closed sets, but a priori, if I have in mind the convex separation theorem, it's not enough in order to separate them. The idea is that formulating this condition in an equivalent way, this way, you have a closed one, a compact one that have an intersection that is equal to empty set. We are typically in the framework of the convex separation theorem that will allow us to, so if I am in this situation, what we are going to do just after in the following, I will have K, I will have my delta here, and I will separate them by something like this. This is the convex separation theorem, this way. I have one of them that is compact, that is delta here, closed and bounded. This one that is a vector space, so that is not bounded for sure, okay, because it is a vector space. And I can separate them by a line if I do a picture on the board, okay? And if I do a picture in a space of dimension n, it will be what we call an hyperplane, okay? That is just a vector space of dimension n-1 in a vector space of dimension n. So I have proved my lemma 5 here. And now I will just do a reminder concerning these things here before to state the convex separation theorem. We're doing some comment concerning linear mappings in my framework here. So may I erase everything except the lemma 5? Yeah?
But if T tilde is in delta and K, then it's not empty.
Yeah? I totally agree with you. But what was your initial hypothesis? If there is an element that is not zero here, you prove that there exists an element here. So you prove this implication here by contraposition. Okay? Yeah, the conclusion, in fact, I agree with you, is that you have an element in this intersection. Okay? But it's not what you want to have because you do a contraposition reasoning. If I suppose this one not fulfilled, this one won't be fulfilled. May I erase, or you have some more questions? Okay? Okay. A kind of notation, or let's say it is a reminder. Okay. So I consider E and F two vector spaces. I use the following classical notation: L, C, E, F. So it's the set. So I just use the same notation than the one you will have in the lectures note. Okay. So it's the set of the phi from E into F such that phi is linear. So it's for the calligraphic L, linear, and the C is for continuous. Phi, continuous, so linear and continuous. If capital E is of finite dimension, if you are linear, you are continuous, but a priori it's not the case. Not the case in grid generality. Okay. You have the linear mappings that are continuous from capital E into capital F. Okay? What happens if I take for F the real numbers? Do you remind the name of this? Linear mappings with values in R here. It's continuous linear form. Okay? They are just linear, continuous, but with values in a vector space that is of dimension 1 here. Okay? If I am of finite dimension here, okay, you have a result that link the dimension of my image, the dimension of the kernel. You remind this result in linear algebra? The rank theorem, theorem du rang? The dimension of the image of phi plus the dimension of the kernel of phi is equal to the dimension of what? Yeah, capital E. Okay, I have this one. Theorem du rang. And in the case where f is equal to r, what is the dimension of my image here if I have a linear mapping that is not 0? The dimension of my image is equal to 1 in this situation if I work with a linear mapping that is not 0. So if r is equal to r, the dimension of my kernel is n minus 1. So let's say dimension of t minus 1. And so what we call the kernel of phi, and I remind you the definition, it's the set of the x belonging to E such that phi of x is equal to 0, where we have in this situation here what we call an hyperplane. An hyperplane is just a vector space with a dimension that is just minus 1 the dimension on the space of the space we work with. Okay? So typically, if I am in dimension 2, an hyperplane will just be a line. Okay? If I am in dimension 3, you will have a plane. In dimension 4, something of dimension 3, and so on. Okay? So it's an hyperplane here. Okay. So it is just, okay, a little reminder concerning linear algebra. But I want to come back to my point here. If I take for E, this one, okay, omega fp, here I have the power set of omega, and in fact, I have already said that this space is isomorphic to R to the power the number of elements in omega. Because here, a random variable in this situation is just a vector with this number of coordinates, meaning the fact that you have to give the image of any element in omega. It's the only condition you have. So if E is equal to this one, okay, I said the following. For x belonging to E, so I have a random variable this way, I can write x in the following way. We can write x of W that is equal W, excuse me, it's the sum of on all the elements belonging to omega of what x wi indicator function wi w. Okay, I have written nothing here. What I have written here is that xwi or xw is equal to xwi if w is equal to wi. Okay, so I write nothing. Okay, I can express this one as a linear combination of indicator function, and I repeat that the meaning of this one just means that when w is equal to wi, xw is equal to xwi, simply. Okay. But if I have phi in this space here, I know that phi is linear, and here I have constant here, so I can write x, or I can write phi of x in the following way: the sum wi belonging to omega of x wi, okay, phi of indicator function of this mapping. Okay. You agree? But in this equality, I can multiply and divide by the probability of wi. Okay? I have the right to do because I have strictly positive terms here. And so, if I express the things this way, in fact, I make appear an expectation. I make appear an expectation because here I will have a random variable and I multiply by the probabilities related to all the elements of omega. So I can write it as the expectation under P of what? Of x times z, where z of w is equal to phi of indicator function of w over p of w. So to say what? That in my situation here, in my situation, linear forms are just weighted expectations. Expectation of my random variable weighted by something here. That is not necessarily a density, but a random variable, okay, that is here just in L1. Okay? So general reminder on linear algebra. In my particular situation, I just say that linear and continuous mapping from in to R when E is the set of the random variable on omega fp here, I can write a linear and continuous mapping from in to R as the expectation under P of x times the random variable z, define this way. Okay. And to finish my reminder, so keep in mind that an element here can be expressed as a weighted expectation of x. So I will erase this one. convex separation theorem. So if I remind you have a course of, it's possible for you to take a course of convex analysis, no? Or functional analysis? No? Well, it's a so-called result, okay, from this course, but here in a very, very restrictive framework, okay? So for my course, okay, even if you don't follow this one, okay, you just have to have in mind what we are going to see together, okay? I will need, in fact, this version for this proof and another version for another proof of another important result. So, in a Banach space B, so what is a Banach space? It's just a vector space that is complete, okay? A vector space that is complete. So in a Banach space B, if A1 and A2 are two closed subsets, one of them being compact, then there exists phi that is linear and continuous from B into R. There exists alpha different from 0 such that in fact you can separate A1 and A2 by phi in the following way. For all A1 belongs to A1, phi of A1 is strictly less than alpha. And for all A2 belonging to capital A2, phi of A2 is strictly greater than alpha. And if I do a picture, so suppose that you have, for example, A1 that is compact, you have A2 this way, that is not necessarily compact, so two closed, so excuse me, I have forgotten two closed convex separation theorem if I don't impose convexity, okay? So two closed and convex, so this one, be careful because I don't have something that is convex here. I'm going to do a nice picture. This one, this one. So you have here, if I am on the blackboard, okay, and a fine hyperplane will be for me the translation of an hyperplane in dimension 2 that is just an affine line. So you have here phi equal to alpha. On this part here, phi strictly less than alpha, and phi strictly greater than alpha. Okay? So you can separate the two closed and convex sets, one of them being compact, by an affine hyperplane here that is represented in dimension 2 by my little picture. So this is the convex separation theorem. So the proof is not that complicated of this one, okay? First you do the proof for A1 being equal to 1 point, and it's not that complicated because you can have the distance between the point and A2, and in fact after you use the compacity property, okay? in order to pass from what happened for one point to what happened for one element of capital A1. But whatever, it's not my purpose. So the convex separation theorem. So in this course I will use two versions. And this one that is the more strict, the one where I have a strict separation between the two closed and convex set, one of them being compact. And I will finish for today with the following. That is the lemma 6. The lemma 6. But in fact, where I said nothing, in fact, it's just using all the remainder I have done. So I keep my picture, I erase this one here. Lemma 6. I said that NA implies the fact that there exists phi belonging to linear and continuous from L0 of omega Fp into R, such that there exists phi, there exists alpha strictly positive, such that for all k belonging to calligraphic k, phi of k is strictly less than alpha, and for all y belonging to delta, phi of y is strictly greater than alpha. And I have nothing to prove to state this lemma. Why? Because we have seen together in the previous lemma that NA is equivalent to the fact that calligraphic K intersected with delta is empty, or excuse me, it misses something in my convex separation theorem. I have done this picture here. What is missing in my statement?
Intersection must be.
Yeah, because okay, if you take this one and this one, it will be really complicated to separate them, okay? So in a Banach space, if N1 and A2 are two closed, let's say, disjoint, closed and convex subsets, then I have my result. So what I have here, I know from lemma 5, so two disjoint, closed and convex, one of them being compact. So I am in lemma 5 in this situation. I have said that NA is equivalent to the fact that calligraphic K intersected with delta is empty. Closed and compact, both are convex, intersection is empty. I have the right to apply my result. There exists a linear and continuous mapping from the Banach space I am interested in, that is the set of the random variable, into R with this. Okay? And I will finish by this today, just keeping in mind that in my situation, according to what I have written here, I know what is the form of this linear and continuous form here. They are just weighted expectations. Okay? And we are going to start with this one next session. Okay?